Hello there, welcome to section 2 of unit 1, and in this section we'll be doing dimensional analysis. Let's look at the objective of section 2. We have 5 objectives here, and the first one is to be able to identify the basic units, the basic quantities with their dimensions. 2. Write down the dimensions of physical quantities. Use dimensions to derive the units of other physical quantities, and also use dimension to check the correctness of an equation. Use dimension to discover functional relationships. Dimension analysis. So dimensional analysis is the analysis of the relationship between different physical quantities by identifying their base quantities and units of measure, and tracking this dimension and calculations or comparison are performed. And dimension analysis is very important because we use to confirm that units are the same. It also helps us in performing mathematical calculations smoothly. Let's look at the fundamental or base quantities that we'll be using here. And here we are going to let me use a laser pointer. We are going to use mass, and it's represented as what? A big M. Use length, and it's represented as what? A big L. And also use time, which is represented as what? A big T. So the distance D between 2 points has the dimension of what? Length, big L. And anytime we are writing this is how you are going to write it, and we are going to represent it. If you are writing the length, the time, or the mass, you put it in a big square bracket like this, and you denote it by its dimension. Now let's look at some calculations using dimensions. First, we'll be doing for area, volume, and density. And I hope you do remember what mass represents, length represents, and time represents, because it's very essential here. Let's look at the dimension of an area. So we know that for area, the formula is length times breadth. So after writing the formula, what you have to do is to just represent the dimension of each of them, the parameter that is there. So for the dimension of length, we just put it in a big bracket like this, square bracket like this, and that of breadth. But in dimensions, we know that length is represented by big L, and breadth is also represented by what? Big L, because they are all what? Distances. When you multiply the big L times the big L, we are going to get what? L squared. So the dimension of area here is what? L squared. Very simple. The same applied to volume. We know that the formula for volume is length times breadth times height. And with this, they are all measuring what? Distances. So the dimension for this is going to be L times L times L. And we are going to get what? L cubed for this. Let's be a little bit dicey and move to density. The formula for density is mass over a volume. You put it in a nice big bracket like this. And we know that the dimension for mass is what? Big M. Because we are measuring what? Weight, or let's say grams. The unit is grams, so it's big M. And we know that from the previous calculation of the volume is what? L cubed. So the final dimension for density becomes what? Big M per L minus per L cubed. So it's either you write it big M, big L minus raised to the power minus 3, or you can write it as big M per L cubed. As we can change the quantity to dimension, the same way we can use the dimension to find the unit of that quantity. We know that for time, the unit is seconds, for mass, the unit is kilogram, and for length, the unit is meter. So supposing that we are given the dimension of length as L squared, and you are asked to find the unit of area from its dimension, you just have to look for the unit for each of the dimension that is given in this parameter. We know that L squared is equal to what? L times what? L. And L here is representing what? The length, which has a unit of what? A meter. So we have M representing a meter and M here representing a meter. This time around, there's no need for you to bring a square bracket. You just leave it like this. And when you multiply M by M, you are going to get what? M squared. That's meter squared. The same thing implies for the volume. Should in case we are given a dimension of volume as L cubed, and we are asked to find the unit of volume, you know that the L cube is what? L times L times L, which the L represents what? A unit of meter. So because we have L times L times L, it's going to give us M times M times M, which is going to give us M cube. Let's look for that of density. For density, we know that the dimension of density is M L raised to the power minus 3, or M per L cube. From here, we know that our M here, the unit is what? Is kilogram. So we just have to write our kilogram, and we know that the L raised to the power minus 3, the unit is what? Meter raised to the power minus 3. So that we get what? Kilogram per meter cube. We can also use dimensional analysis to check the validity of an equation. So here we have one equation that we'll be seeing in our following sections, where we have x as the distance is equal to velocity times time plus 1/2 acceleration time squared. Here, for us to be able to check the validity of this equation, for every part, say the x, the v0 times t, the 1/2 at squared, each of them is separated by s equal to and a plus, and it can also be a minus. We have to know that for each individual terms here, we have to find the dimension. So let's name the first term as 1, second term as 2, third term as 3. And note that each term here is separated by what? A equal to and a plus. It can be separated by a -2, but not multiplication and division. So let's find the dimension of each of the terms here. Let's pay an attention here. So for the first term, x, that is what? Distance. Because we are measuring distance, the dimension for distance is going to be what? Big L. Let's look at, we put this one too in a square bracket nicely like this. Let's look at the second term, that's v0 times t. v0 is the speed and t is what? Time. The formula for v0 is what? Distance over time, that's velocity. So distance is L and what? Time is what? T. So distance is what? L and time is what? T. So the whole of this dimension that we have here represents the what? The v0, that's the velocity. And t here is what? Our big T, that's the time. When you multiply these two, this t is going to cancel this t, and you are going to get what? Our L as a final dimension for v0 times t. Let's move to the third term, term 3. We have 1/2 multiplying a t squared. Acceleration, the formula for acceleration is what? Velocity over time. When you divide velocity over time, we are going to get what? L over what? T squared. And we already have a t squared here, which the dimension is going to be big T squared. So that our final dimension is going to be what? The t squared is going to cancel out, and the final dimension for 1/2 at squared is going to be L. Let's forget about the 1/2 here because it's dimensionless. So from here, because we have all the term L, x the term 1 to be L, term 2 to be L, and term 3 to be L, we say our equation is valid or what? Correct. Let's look at a second example here. Still checking the validity of an equation. And this time around, the equation given here is x equals v0 squared plus at, where our x here is the speed or the distance, the v0 is the velocity, the t is the time, and a is acceleration. As explained earlier, we are going to group this one in terms, and grouping it in terms equal to minus and plus is used to group them. So first we can take this one as term 1, we have equal to sign here. Take this one as term 2, we have a plus sign here, and take this one as what? Term 3. We can't use multiplication and division in grouping it because a is multiplying t, right? But we didn't divide it, as a is term 1 and t is another term. So after getting our terms here, we have 3 terms here. We find the dimension for each term. Already we know from the previous one that we did that the dimension for x is what? X is what? Is L. Let's look at the dimension for the second term. That's v0 multiplying t. We know that the formula for velocity is what? speed or distance over time. And distance, the dimension for distance is L, and that of time is what? Is T. Multiplying, which is going to be multiplied by what? T squared. So here there should be a squared here, which is going to multiply by what? T squared. So when this T cancel T squared, we are going to get 1T here remaining, and the final dimension is going to be L multiplying T. Let's look at the term 3, AT. We know that the dimension for acceleration is L over T squared, and we have T as this already. So we are going to get the final dimension for AT as L over what? T. Looking at the dimension of the individual terms, that's 1 L, 2 LT, and 3 L over T. We can say that the dimension for this equation is what? Invalid or incorrect, because at the end we should be getting the same dimension across each term. Well, another big advantage of dimension analysis is to be able to use it to find constants in equation, and we'll be taking this example here. So for here, we are given a gas equation as P plus A over V squared, in a bracket, another bracket open, V minus B, or in a bracket close, equals RT. So here we have P as the pressure, V as the volume, and we have a constant A and B to be calculated for. It is very simple here. Just pay attention and try to understand. We just have to find the dimension for P and also find the dimension for volume before we can find the dimension for the constants A and B as we are requesting. Before we do that, let us try to understand something before we can go on with this. Should in case we have 1 meter plus 1 meter, is it possible for us to add this together? Yes, because they have the same unit, so that we get at the end 2 meters. In case we have 1 meter, that's length, plus 1 kilogram, is it possible for us to add this together? No, it's not possible, because they have 2 different units here. The same thing applies to the equation that we have here. Pressure here is being added to here, to A over V squared, because they have the same what? Unit, or the same dimension. V here in this equation is being subtracted here with the B, because they have the same unit and also the same what? Dimension. So let's look at how we can go about this. What we have to first do is to just find the dimension for P and also find the dimension for V. We know that the formula for P, that's pressure, is what? Force over area. So after writing the formula, what we have to do is to also find the dimension for force and also for area. We know that force 2 is also equal to what? MA, right? And we also know that area is equal to what? Length times what? Breadth. It's not the dimension I'm writing. So from here, we can also find the dimension for A. The dimension for A acceleration is what? From the previous one that we did, is L over T squared. So that the dimension for MA will give us, M will give us a big M, and A will give us what? LT minus 2. And the dimension of area will give us what? L squared. If we bring this one up, then it means, or we just cancel the L together so that we get only 1 L left at the denominator. We get the final answer to be big M, L raised to the power minus 1, and T minus 2. I think it's very difficult using the mouse to write it. So that the final answer will be this. So this is the dimension for pressure. And the dimension for volume is what? L cube. Now, let's look at how we are going to go about it to find our constants A and B. Because we have P to be equal to, P plus A over V squared, we have the P to be separating the A over V squared with plus, meaning it has the same dimension, right? And the same unit. So we can also write this as P equals A V squared. From here, I think we can just make A the subject before we substitute the dimensions inside. So that our A here right now becomes P multiplying what? V. We know from our dimension that the dimension for P is what? M L minus 1 T minus 2. And for V is what? L cube. So that at the end, we will be getting, pardon me here, the PV here is PV squared. So the L right now, we know the volume to be L cube. So multiplying by 2, we are going to get what? L raised to the power what? 6. So let me correct this one here. So that at the end, we get we have L minus 1 here already and L6 here. So the minus 1 from the 6, we get what? We get 5. And we bring our what? T minus 2. And that is what we have here. Very simple. So from here, we can say that the dimension of A is the whole of what we have here. And you can use this one to determine the unit for what? For A. I think it will be a nice trial for you to do. The second one too is for the B. We know that because we have a minus sign separating it, it means V and B has the same what? The same unit and the same dimensions. So we can just write V to be also equal to what? To B. So that we know that the dimension for V is what? Is L cube. So straight away, we can say that B, the dimension of B is also what? L cube. You bring your square brackets, which is very important.